Muy bien, bienvenidos a todos, bienvenidos al inicio de un nuevo seminario a lo largo del curso, Seminario de Historias Matemáticas, que empezamos. Me alegro de que nos volvamos a reunir aquí en ocasión de estas conferencias que a lo largo de todo el año nos hacen deleitarnos realmente y pasar muy buenos momentos, aparte de ver a muchos antiguos profesores que hoy, por lo que se ve, han faltado. El sector más longevo no ha venido todavía. Bueno, les quiero presentar en primer lugar a los miembros que están sentados conmigo en la mesa. A mi izquierda, el profesor Frayudoun Rezakhanlou, de la Universidad de Berkeley, que es el que va a ser nuestro conferenciante. A mi derecha va a estar el profesor Álvaro Pelayo, que va a hacer una presentación del profesor Rezakhanlou y que, bueno, le conoce muy bien, puesto que han estado trabajando durante los últimos 17 años conjuntamente. Y a mi derecha, en último lugar, pero no menos importante, la directora del Seminario de Historia Matemáticas, la profesora María Emilia Alonso, a quien, tanto a ella como a toda la comisión, le agradezco el trabajo que ha hecho por volver a crear un nuevo ciclo de conferencias para este curso 25-26. Bueno, luego hará el profesor Álvaro Pelayo una presentación del profesor Rezakhanlou más profundamente, pero yo creo que tenemos hoy un gran privilegio de tener una figura tan importante como la que tenemos y que nos va a dar una conferencia que estoy seguro que vamos a disfrutar. Thank you very much for agreeing to participate in this history seminar, which is very important for our faculty and is one of the most important activities for us during the year. No? Professor Rezakhanlou is a great expert in several areas of mathematics, mainly probabilistics, statistical mechanics, and symplectic geometry, and also in partial differential equations. After my words, Professor Álvaro Pelayo will give a more in-depth presentation about the work and the history of Professor Rezakhanlou, and from me, simply thank you very much once more for agreeing to participate. And I wish you that we'll be delighted with your talk. Thank you. Then, en primer lugar, voy a pasar la palabra ya, a la profesora María Emilia Alonso para que se dirija a todos nosotros cuando quiera. María Emilia.
Pues os doy la bienvenida a la inauguración del Seminario de Historia. Hemos intentado tener temas diferentes y este tema realmente es nuevo y tenemos varias innovaciones este año. Una es la inauguración, que tenemos el honor de contar con el profesor Frayudoun Rezakhanlou de la Universidad de Berkeley, y del cual tiene una larga trayectoria de trabajo el profesor Álvaro Pelayo, que va a hablar ahora para hacer una presentación personal. Luego tenemos varios hitos que celebramos este año. Uno es el centenario de la mecánica cuántica, que David Pérez García nos dará una charla, y otro es el 30 aniversario de la demostración del teorema de Fermat. Luego, además, hay otras charlas variadas. Y mirar, el éxito de este seminario, ¿sabéis cuál es? Es la 46 edición. Si consiguiéramos que la media de edad esta no superase de los asistentes 46, sería realmente un éxito este año. Así que, sin más, y bienvenidos, os dejo al profesor Álvaro, que va a presentar la obra del profesor Rezakhanlou.
Muy bien, muchas gracias, María Emilia. Creo que cada año lo tendrás más difícil con lo de la media, ¿no? Pero muchas gracias por tus palabras. Y enhorabuena, y gracias por todo el trabajo a ti y a toda la comisión. Y ahora, cuando quiera, profesor Álvaro Pelayo.
Ok, muchas gracias, decano. Y estoy muy contento de estar aquí hoy y de que Frayudoun esté dando una conferencia, y muchas gracias, María Emi, por presentarme. Como sabéis, el decano y yo apoyamos este seminario con gran entusiasmo, y a mí me parece que como he dicho muchas veces, que es una de las actividades realmente importantes de la facultad. Vale, y ahora me paso a inglés para que Frayudoun sepa lo que estoy diciendo de él, ¿vale? Voy a hacer una presentación muy breve de Frayudoun, unas pocas líneas. Frayudoun Rezakhanlou is, as the dean said, professor of mathematics at the University of California, Berkeley, and he is a world expert in statistical mechanics. He has made major contributions to a diverse range of subjects in using a combination of techniques from geometry and analysis. He has a very strong geometric intuition, and he has an extraordinary technical power in the fields of probability and PDEs. He is widely recognized as one of the pioneers in introducing probabilistic methods in symplectic geometry. His work has been recognized with many awards, including the J. Krakauer Award from the Graduate School of New York University, a Sloan Fellowship, and he has also delivered prestigious endowed lectures in the United States, such as the Robert Lectures at Washington University in St. Louis, and I had the pleasure of attending these lectures. You remember Frayudoun, right?
Yes, yeah. I do.
And as well as the Charles Amick Lectures at the University of Chicago. His students include leading mathematicians, for example, Alan Hammond, who is an expert also in probability, is now also full professor, if I remember correctly, at the University of California, Berkeley. Right? Full professor?
Right.
Yeah, full professor. So you can see Frayudoun's influence has been very extensive. Also, he has an excellent relation with Madrid. He's been to Madrid 4 times. I think the 4 times visiting me, is this correct? Yes, correct. At various settings. And we started collaborating about 17 years ago when I was at the time a young assistant professor visiting assistant professor at UC Berkeley. So this was around 2008, 2009, and we have been collaborating for the past 17 years. And even though we work a lot, we only have written 2 papers, but we're very proud of these papers. And so this is all. It is a great pleasure to have you here, Frayudoun. I hope this will be the 4th, but there will be many more times that you will be here. And he's also a great speaker. And as I said, one of the very few people who is a specialist in probability and PDEs, as well as symplectic geometry. So it's an honor to have you here, Frayudoun.
Thank you very much.
Muchas gracias. Pues entonces vamos a pasar a la conferencia Boltzmann, Statistical Mechanics and Hilbert SixthProblem. Professor Rezakhanlou, please.
Thank you very much. Okay, let's see if you can. Okay, so let me start with a disclaimer. I'm not a historian. And another disclaimer, this is the first time I'm giving a talk in a history seminar. And I was kind of wondering why Alvaro asked me to give such a talk, but then I figured that if you have enough gray hair, then you qualify for such activities, such seminars. And I'm going to use both slides and boards. I wanted to use the boards only, but I figured that, Alvaro asked me to show pictures. So I produced many pictures here, and I'm going to share those pictures with you. So I'm going to write also many math formula. So hopefully I have enough room. I'm going to fit everything here. In fact, to kind of start with maybe alternative title, the alternative title would be The Tale of 3 Boxes. I'm going to draw 3 boxes here. And for more excitement, I'm not going to tell you what these boxes are for. To know what these boxes have to do with my talk, you have to wait till end of the seminar. So I use this trick to make sure people stay till end, based on some of the experiences I had from before. Okay, so let me start with a picture. This is Bernoulli. He is responsible for what we regard as kinetic theory of gases. And what he had in mind was that the idea was that you may regard a gas to consist of a huge number of particles. Now we know that the number would be like Avogadro number, something like 10 to 23. And you can use this microscopic picture, a system of many moving particles, to explain things like the temperature and the pressure of a gas. For example, if you have a surface, if you want to explain, you want to calculate the pressure on the surface, then this picture would be very helpful. So now I'm ready to write something here. I call this microscopic. Okay, it's just motivated by this idea. So if I want to say something about the microscope, so this would be a picture for a gas or a fluid. Gas or fluid. And in the microscopic picture, I have the model that, so let me also write here, microscopic world. So in the microscopic world, what I have is a system of, we have N. N is very large. For a fluid would be 10 to 23. For a dilute gas would be like 10 to 18, for example. N particles of positions x1, xn, and I'm going to put here, to make it sound very mathematical, I put here RD. D is 3 in reality, but you can imagine that, for example, you can have a kind of a fluid that looks two-dimensional, or you can have a fluid or a gas in a pipe, so it's like one-dimensional. So D could take other values. So you have positions and velocities, v1, vn, so these are vectors, again in RD. And each particle travels according to its velocity, and particles are interacting. A standard model for the interaction is that you are given a potential function responsible for the interaction between pair of particles. So it's often the case that a function v, this represents the pair potential, is given, and for many problems of model, for example, if particles are charged, or if you consider the gravity between particles, n as a function of xi and xj would depend on the difference, and in fact, more is true. This is going to be a function that depends only on the distance of particles. And the way to think about it is that you have a picture like this for W. You know, the W is the potential, could look at different forms. But for some of the formulas that I write later on, you can think of W something that is of compact support for simplicity. So maybe it looks something like this. And then I want to write the differential equation here. So let me continue here for the microscopic world. In fact, the equation, so all these boxes would consist of differential equations. For this box, that would be Newton's equation. And the equation reads as each particle travels according to its velocity. So I assume the mass is 1 for simplicity. And the velocity is changing based on the interaction between particles. So you have a picture like this. In fact, it's more convenient to put a parameter here. So I'm going to modify this picture and put here epsilon. So I introduce a parameter epsilon. So you see the model that I'm describing for this box consists of various parameters. One is the total number of particles. This is a huge number. The other one is the potential governing the dynamics between particles. And the third one is this epsilon. Epsilon is the range of interaction. So here, epsilon small, the range of interaction. So this is this box. So you want to kind of solve this equation to understand what's going on for a gas, to a gas, or a fluid. But you can imagine the challenge has to do with the fact that n is enormous. Even if you manage to solve this equation, you don't know what to do with that data. And that was something that people were wondering about, and that is responsible for the birth of statistical mechanics. Between 1859 and 1866, James Maxwell developed a theory for a gas that is at equilibrium. So he started with this picture of Bernoulli, and he was wondering whether he can say something about the gas at equilibrium and use that to explain the properties of the gas. And he suggested that perhaps we should use statistics to understand such a gas because of the size of the model. Since n is very large, you don't care about the exact locations of particles and exact velocities, but rather statistical questions. For example, if you give me some region in space, what fraction of particles at a given moment would be in that space? These are the relevant questions that you can address. And in fact, according to Gibbs, he was the first physicist who tossed the word statistical in this context, and that led to the notion of Maxwellian. So this is the exact quote from Maxwell. It says, in dealing with masses of matter, while we do not perceive the individual molecules, we are compelled to adopt what I have described as the statistical method. This is the first time the word statistics is used in this context of calculation, and to abandon the strict dynamical method. Dynamical method meaning solving Newton's equation exactly, in which we follow every motion by calculus. So we want to give that up and use the statistics to address questions. And in fact, let me say something about Maxwell. Since I want to write many formulas, what Maxwellian is, Maxwell suggested the following formula based on very formal calculation, no rigorous mathematics, for the statistics of a gas at equilibrium. And the formula he gave for the velocity of particles reads as this. A given rho, this is the mass density, the vector u, this is a velocity, and temperature, theta. Consider, so I want to write a density function that represents the density that a typical particle takes the velocity v. And it looks like this. Would be m is a function of v, but of course this m depends on your choices. You see, different gases, they can have different density, different average velocity, and different average temperature. So given these parameters, you can build your Maxwellian. So it does depend on these parameters. And it reads as this, rho divided by 2 pi theta d over 2e minus v minus u squared 2 theta. And if you are a physicist, you put some dimensionless constant, or this is the gas constant, meaning it varies as you go from one gas to the other. So if you're a probabilist, you may recognize that this is the celebrated Gaussian density. So what probabilists call it Gaussian density or Gaussian law, physicists call it Maxwellian because it does represent the probability density of the velocity of a gas at equilibrium. Okay, so that was the contribution of Maxwell. And then here comes Boltzmann. In 1864, he was only 20 years old. he discovered this paper of Maxwell. He got very much interested in the paper, and he devoted his career developing the ideas that started from the work of Maxwell. And that led in 1870s to the development of statistical mechanics, a remarkable collection of works that we're still working on them. And he kind of gathered all these ideas in lecture notes known as Lectures on Gas Theory. That was like published in 1896. However, his theory was not accepted at all. He was in Vienna. Ernst Mach, a physicist working on fluid mechanics and other things, also was in Vienna, and he was totally against Boltzmann's work. And he criticized Boltzmann's work because it was based on the theory of atoms. This is late 19th century. The theory of atoms was not confirmed in physics. So it was like a theory like other theories. And Mach's problem was that even though Boltzmann managed to use his ideas of using this microscopic picture of particles to explain entropy and doing thermodynamics, but Mach argued that they were just theoretical constructs and lacking direct observable evidence, and dismissed it as fantasies. And Boltzmann took it very hard. He found later on in his life to prove that his theory is valid and is a good theory. But unfortunately, that didn't help him so much, and I think that contributed to his depression, and he committed suicide by hanging. He was only 62 years old during a vacation. So that's the work of Boltzmann. So let me tell you, a little bit sad, I know, but so this is the work of Boltzmann, mesoscopic picture. So you have microscopic picture, mesoscopic picture. This is my second box. And the main outcome here is yet another equation. So you had here Newton's equation, and here you have Boltzmann equation. And remarkably, this equation goes beyond Maxwell's equilibrium description. It describes gases at non-equilibrium. However, this picture is called mesoscopic because it deals with rarefied gases, dilute gases. And what's happening is that if the gas is sufficiently dilute, there are not many interactions, and certain mathematical tricks, they become available. And he used those tricks to derive yet another equation, but not for the whole collection of particles. So this is two details and not very useful. He suggested a reduced description involving only the density of particles of given velocity. So that was his idea. So this is a reduced description. You ignore some of the details of the model. You just focus on the density of particles, and then you have a simpler equation. You don't have to deal with 10 to 23, or in the case of a dilute gas, 10 to 18 many parameters. So perhaps, so that's microscopic word. Maybe I erase this and describe my mesoscopic word, and that would yet another differential equation, and you have to compare it to this. And the whole statistical mechanics, or at least this part of the statistical mechanics, has to do with the interaction between these boxes, why they are related. After all, they are dealing with the same object, namely a gas, a fluid. Why they are related, even though they look completely different on the surface. So that is the whole idea. So now perhaps I erase part of this. Now I want to tell you about the mesoscopic world. A la Boltzmann, that's what Boltzmann did. And first, Boltzmann, in fact, considered a simplification of this model. It turns out that if your potential is short range, you can replace your model with a simpler model. So let me first make a remark before I get into it. So I want to say something about mesoscopic world. First, observe we have the usual conservation laws. Mass in the sense that this is a closed system. No particle is created, no particle is destroyed. They're just interacting, moving according to their velocities, and interact once in a while. And the momentum, since I'm assuming for simplicity masses are equal, that means if you look at the sum of VIs, the sum of velocities, that doesn't change with time. And the kinetic energy. I'm sorry, not kinetic energy. You can have V here, but let me say just energy. So these guys are conserved, but so the above equation, let me call this 1. In 1, we have a so-called soft potential. That's what physicists call it. For many purposes, you can switch from soft potential to hard potential, which means that if the range of interaction is finite, we may switch to hard potential, which basically looks like this. So soft potential, remember your W look like this. This is your W. This is soft. For the hard potential, you make it like this. So here is infinite, here is 0, meaning that you regard if, so remember W has to do with the way it appears here. The potential is given by W of the distance between particles. So this means that if particles get too close to each other, you regard it as infinite energy. And if particles are not too close to each other, it's as if there is no potential. So in other words, the interpretation is that they move freely with no interaction until they get close. And when they're too close, they cannot get closer, because the region associated with closer distance is forbidden. After all, the energy is infinite. Since you have conservation of energies, if you start with finite energy, you cannot get too close, because then you violate the conservation of energy. And you can kind of play with this. You start with this, with soft potential, and make this the kind of amount of energy, potential energy you have, you converge it to infinity, and you figure out what happens. And the way to figure it out is that, well, basically, you have the conservation at interaction. You have the conservation of momentum. You have the conservation of kinetic energy, because off of this region, you only have kinetic energy. And since the potential depends only on distance of particles, you also have the conservation of the so-called angular momentum. You put all these conservation laws together, then the following picture emerges. So this is hard. So for hard potential, in fact, you end up playing billiards. So the model would be nothing but billiards. And that's exactly what Boltzmann considered for simplicity. So we basically have billiards. Let me explain what that means. It means that you may regard each particle as a ball of diameter epsilon. So what you have here as the position of particles that I mentioned before, the position of a particle would be the center of such a ball, and each particle has a velocity vi. So the balls, different balls are moving according to their velocities, but once in a while, two particles collide. So imagine you have one particle of position center xi, you have one particle of position or center xj. They collide with velocities vi and vj, and then something happens after the collision, and they gain new velocities, v prime I and v prime j. And you can figure out exactly what the new velocities are using all the conservation laws. And it's easy to explain what's going on. So imagine you have one ball of velocity v, one ball of velocity v star, and suppose they collide like this. If you respect all the conservation laws, all happens is that the velocity of these two particles are exchanged. So afterwards, they have the opposite velocities, they have the other velocities, and then they move away. Now imagine you have two particles that collide like this. Then what happens is that you look at the vector connecting the centers, this vector, call it Nij. The unit vector connecting the centers, epsilon is very small. And these vectors, all they do, they interchange the component of the velocities that is in this direction. And the other components, they stay put. They do not change. That's all happens. So if I want to write down a formula for it, would be v prime I equals vi minus vij nij nij. I explain what, oh, you cannot see it, I guess. Let me erase this. So this now is replaced by this. So vi and vj becomes v prime I and v prime j. This is when xi minus xj is exactly epsilon. That means they are meeting like this, they are colliding. Note that the distance between these guys would be exactly epsilon because the diameter is epsilon. And then v prime I is given by this recipe. So Boltzmann decided to play some billiards to understand gases. And he came up with the following differential equation. So let me erase this. So let me tell you what Boltzmann equation is. So now I want to explain what this equation is. Very fundamental equation, valid for rarefied gases. The equation goes like this. If Fxvt is the density of particles of velocity v at position x and time t, then I'm going to write the differential equation for it. The time derivative of f plus v times the space derivative of x, this has to do with the fact that each particle travels according to its velocity, equals to, maybe I just write down what this guy does, equals to f prime, f v prime, I explain what that means, f v prime star minus f v star times v minus v star dotted with n, the positive part, dn dv star double integral n equals 1 rd. That was his equation. And let me explain what's going on. It says the following. You want to know how the density of particles of given velocity is changing. So you look at those particles and you ask yourself, if this density want to decrease, how that happens? It decreases if a particle of velocity v collides with another particle and it changes its velocity. That would be responsible for the loss. And Boltzmann argued in the following way. It says that, well, if I want to see a scenario at position xt, when I have a particle velocity v and a particle velocity v star, since the density of particles more or less represents the probability of finding such a particle. After all, if the density is high, that means more likely to find such a particle. Density low is less likely. So you should think of fxvt also representing the probability that at position x at time t you find the particle of velocity v. That's the intuition. And then Boltzmann argued that since the gas is sufficiently dilute, not much correlation is built. Therefore, to have such a scenario, you just have to multiply the probabilities. This is the probability of finding a particle of velocity v. This is the probability of finding velocity v star. This product of probabilities represents such a scenario. And of course, this is not true in reality. But he's a physicist. He says that, well, in ideal world, such thing should be true. If it's not true, you're making a very small error. And that small error, we know how small it is, has to do with the size of the system, how many particles you have, and the size of epsilon. So in fact, he tossed the word Stoß-Zahlensatz. For such a phenomenon. He made an ansatz. He made an assumption. The assumption was that particles, before collision, they act as if they are independent, as if they forget about the history, as if they are in a chaotic situation. So Stoß-Zahlensatz, I think the translation would be the assumption of molecular chaos. So you can pretend particles always are in chaotic situation. That's why you get this probability, product of probability. And with minus signs, that means this is responsible for the loss of particle velocity v. And this represents the opposite scenario. You want to create a particle velocity v, you choose some v prime and v prime star they look like this. So you have this v prime and v prime star, and then they collide, and there's this corresponding n, and v is one of the outgoing velocity. And once you have such a scenario, then v would be the outcome, and that's responsible for the increase of density of velocity v. So he wrote this PD as the description here. That was the work of Boltzmann. A very remarkable achievement. Now, I want to get to this box. Macroscopic picture. And here you have Euler and Navier-Stokes equations, yet other differential equations. Maybe it's time to pause. Am I going too fast? Too much mathematics? Enough pictures? So this is Euler. I have many heroes. He's one of them. Boltzmann is the other one. Okay, in 1757, he set up an important collection of differential equations for fluids and gases, known as Euler equation. And later on, Navier and Stokes, Navier, French mathematician, and Stokes, they developed the viscous version of the fluids. That would be Euler equation plus a little bit. That is this. So in summary, you have a huge collection of differential equations. OD is Newton's equation. This is this box. You have a system of integral differential PDE. That's Boltzmann equation. That is this picture. And yet, I have another collection of differential equations here. And the whole story is how these three pictures are the same. And that's Hilbert's sixth problem, to unify these three pictures. So to wit, let me tell you how the Euler equation looks like. And you see these equations on the surface, they look drastically different. Just compare Newton's equation to this equation. On the surface, they don't look like each other at all. Nonetheless, you can get one from the other. And I explain that in a moment. So let me now switch to the macroscopic world. And now what happens is that you focus on conservation laws. What happens is that if you come up with a candidate for the density of a fluid at position x and t, so imagine this parameter, depending on xt, represents the mass density. But this is a local version. The total mass is conserved. After all, the total number of particles is the same. Doesn't change with time. But locally, if you focus on a very small region, the number of particles there is changing with time. So it makes sense to talk about this guy, which is not constant. The total integral of it doesn't change with t, but itself is changing. And u xt, this vector value function, that would be your velocity density. This is a density of particles of given velocity, which kind of resembles what you saw here. And ext, this is the internal energy. Okay? And Euler, remarkably, based on just physical considerations, without no mathematical justifications, write down a collection of differential equations for this equation, for these quantities. Rho u e solves the following system of differential equations. The derivative of rho with respect to time plus rho times u differentiated with respect to x. Maybe I'll put here divergence. This is the space derivative, is 0. This is the conservation law of density, mass density. Rho u, this is the momentum, differential with respect to t, plus the derivative rho times u tensor u. This is a matrix you build out of u, plus something that depends on your fluid. So this is the information that you have to do some calculation to figure it out. So would be, this is the pressure. Pressure depends on the density and depends on the internal energy, equals 0. This is the conservation of momentum. Rho e t plus the divergence of rho e plus p rho e times u equals 0. And E is the total energy. So it's the kinetic energy plus the internal energy. This PDE is what you see for macroscopic picture. This is when the viscosity is too small. If there is a viscosity, then you have to modify the right-hand side here. But I'm not going to bother to write it down. So for conservation laws, you have this picture. For microscopic details, you have this picture. For mesoscopic picture, you have this picture. Okay? Now, we would like to be able to go from the microscopic picture to this picture, from this picture to go to this picture, and from this picture directly to go to this picture. So that's the story of statistical mechanics. How you can achieve that? Is there a mathematical formulation for it? Now comes Hilbert's sixth problem. He basically asked this question. Is there a unified theory for all these three descriptions? So in 1900, Hilbert formulated 23 problems responsible for many research agendas and developments in 20th century. And he presented this in an international conference of math in Paris back in 1900. And later, he gave a more precise formulation of the sixth problem. Basically, he was very much inspired by the work of Boltzmann. And this is what he said in words. Let me see. Can I think maybe I just read it here. So mathematical treatment of axioms of physics. And let me kind of pinpoint, yes. The theory of probabilities and mechanics. He wanted to have a very precise formulation of probability theory. Back then, there was no such formulation. People just, flipping a coin or something, doing some combinatorics. It was not a very precise mathematical theory. And it seems desirable to have logical investigation, rigorous and satisfactory development. And Boltzmann work in principle on the principles of mechanics suggests the problem of developing mathematically the limiting processes. There merely indicates, I'm not saying it, the sentence is so long that I lost track of it, which leads from the atomistic view to the laws of motion of continua. This sentence is very, very mysterious. That's exactly this picture. I mean, he didn't have enough formulation to write it that way, but I think he sensed that there must be a way to go from the microscopic description to Euler equation. That was Hilbert's sixth problem. When it comes to the probability, in fact, that was achieved by Kolmogorov in 1930s. He basically said that probability theory is nothing but Lebesgue's theory of integration and measure theory. That's what probability is. If you have a measure of total measure 1, that's probability theory. That was solved. But the other part, that mysterious sentence, is still a long-standing open question. And we are very far from achieving this. OK, so now the question is, can I have a more accurate formulation of these relationships? What does it mean? What these arrows mean? You cannot reverse the arrows. Why? Because as you go from this detailed versions to this version, you lose information. That's why you can only go this way. How mathematically you can formulate it? If you go from here to there, you lose a lot of information. And how you can go from here to there? What happens is that Boltzmann equation represents a dilute gas. What you can do is that you introduce a parameter known as a Knudsen parameter. Knudsen parameter measures, in average, how long a typical particle waits until a collision happens. And if the gas is dilute, that means you wait longer. If the gas is denser, you wait less. Knudsen constant is exactly how much waiting you have to go through to have a collision. So if you send the Knudsen number to 0, then the gas becomes denser and denser. And then you should be able to derive Euler equation from Boltzmann equation by making the gas denser. That's the idea. So there is a possibility to go from this picture to this picture. This represents fluids. This represents dilute gases, but you can make the gas denser and denser. So now the question is, to make sense of these, how we can make sense of the arrows. You see, if you're a physicist, you have an idea about n, you have an idea about the range of interaction. If you're a mathematician, you're a dreamer. You say, well, n is large, so I send n to infinity. Epsilon small, I send it to 0. That should give me an idealized scenario. And that's exactly how you can achieve these arrows. For all these arrows, you idealize the situation by sending some parameters to infinity. So the question is how you do that. The claim is that here, for example, you send n to infinity, the number of particles. You send epsilon to 0, the range of interaction. However, in order to make sure this gas is not too dilute, there's a relationship between n and epsilon. And what is that relationship? You see, you can imagine that you have a fluid or a gas, maybe in a box. And let's say that for such a gas or fluid, 1/3 of the box is occupied by these molecules, or maybe 1/10 of it. And each molecule you pretend is a ball of diameter epsilon. The volume of the ball, so volume of particle, volume of a typical particle is proportional to its diameter raised to the dimension, epsilon 3 times a constant. That would be more or less the volume occupied by one molecule. And n would be the number of particles. So volume occupied by particles would be roughly n times epsilon d, because you have m particles, each one is of this volume, so that seems reasonable. And then let's say this is some constant lambda, because I want lambda fraction of the box to be filled. So in fact, you send n to infinity, epsilon to 0, but you make sure that, for example, n is exactly, oh man, I'm breaking all these chalks, lambda times epsilon minus d. So that's the relationship between n and epsilon. So now you have a very precise mathematical formulation. You start with n many particles. You start with a potential v, and you send n to infinity, epsilon to 0 in this manner. And in fact, this pressure that appears here, you have to do a lot of thermodynamics calculation to express this pressure in terms of v that appear microscopically. So the potential that appears in the microscopic description should be used. You can use that to determine what pressure function you have in this Euler equation. Once you do that, then you should be able to derive those PDEs from Newtonian mechanics. Do we know how to solve this? Long-standing open question. We have no idea how to do it. The only result that I know of in this direction achieved by Stefano Ola, H.T. Yao, and Raghu Varadan, he managed to prove that provided Euler equation has a nice solution, and we don't know how to prove Euler equation has any nice solution. Even a bad solution, we don't know how to do it, let alone a nice solution. And provided the model, you add some randomness to the model. When you add some randomness, it helps. And provided you replace kinetic energy with an energy functional that looks like relativity. So you make all these changes, then you can derive Euler equation from particle system. That's the only existing results. And removing any of these additional changes wide open. We don't know how even start the problem. It's that hard. That is a question of this direction. How about this direction? Actually, it took a while. People figured out how to do it. And that was achieved by Harold Grad in his thesis. He was student of Courant at Courant Institute. I'm coming from Courant Institute. And he actually figured out mathematically what should be the relationship between n and epsilon. So remember, for a dilute gas, n is much smaller than a denser gas or a fluid. But that is in physics, mathematically what that means. In fact, Grad figured out that the relationship between n and epsilon is not this, but is this. So here you have a formulation. You send n to infinity, epsilon to 0, and you assume such a relationship between n and epsilon, which means that if you are dimension 3, n should be proportional to epsilon minus 2. So instead of the volume, it's as if you just care about the surface area. Then you should be able to derive Boltzmann equation in a rigorous fashion. Do we know how to do that? Still long-standing open question. And let me tell you what was the first progress. For short times, if you assume, in fact, for short time, first, the question is whether I understand Boltzmann equation. One can prove, this is another open question, whether Boltzmann equation has a nice solution, long-standing open question. We don't have the slightest idea to prove that. But if you assume that there is a nice solution, then you can do that. That's the hope. And in fact, if you assume time is sufficiently short, as short as 1/5 of having, is as if the time is short enough that each particle only has 1/5 of collisions, which means you have to wait like 5 units of time to collide once. So that gives you how short that time is. Then Lanford managed to derive the equation in 1975. And last November, I couldn't find the third picture. I worked very hard, but I have two pictures. Yu Deng on the left, and Zahir Hani on the right, and Xiao Mao posted a huge, long paper to claim that if Boltzmann equation has a classical solution, then they know how to derive it via this direction. However, nobody has been able, including myself, to check the proof. And I'm pretty sure if the proof is checked, one of them is still under 40, he would definitely get Fields Medal for it. But we haven't been able to verify the proof. Okay, so that would take care of this direction. Finally, how you go from this direction. So let me explain that, and this is called hydrodynamic. And the idea is that, remember, your Boltzmann equation looks like ft plus v dot fx equals qf. And I put here a number that is known as Knudsen, I can't say this name, Knudsen number. Maybe I should write it down, but I may fail the spelling. Knudsen. Okay? So what happens is that the solution to this equation depends on your Knudsen number. And the idea is that when the Knudsen number goes to 0, which means the gas becomes denser and denser, then the solution fxvt start to look like one of the Maxwellians. But the parameters still depends on remember the parameters were the average density, momentum, and temperature. Then start to look like these. You substitute Maxwellian in here, then remarkably you start to see Euler equation when you substitute a Maxwellian with varying parameters in here. And then rigorously you have to show that indeed looks like this, and indeed these equations are valid in limit. Still long-standing open question. Only in some cases when the fluid is incompressible, we know how to achieve that. Okay, I think maybe, do I have another picture? Since I don't have a picture, maybe I should stop.
Thank you very much for your splendid conference. It was very, very nice and very didactic.
Thank you.
And there are some time for questions, and I encourage the participation of the people, so please. There are a lot of young in this time, so please. Do you have some questions, some comment? Antonio?
Okay, thank you very much, Frayudoun, for your nice talk. I want to ask one question. It's about the death of Boltzmann in 1906. Has his death to do with the fact that Ernst Mach does not accept his ideas, or is independent?
Well, I mean, I think when he got older, his mental condition got worse. And now he's diagnosed based on the symptoms that they had observed. They regarded him as suffering from, as someone who was suffering from bipolar disorder. So he did have some problems, but then, you know, based on things happening around you, your condition can get worse. So for sure, he was very depressed that his theory was not accepted. That's definitely recorded. Whether the suicide is based on that I can't tell. But you know, he was only 62 and he was vacationing, so you can imagine that probably he was extremely upset about many things.
Okay,
Not related to the family, he was there with his family, so I suppose it has to do with other things.
Anyone else? Yes.
Thank you very much, Frayudoun, for the very nice lecture. Extremely interesting material. So I have a question before this major development by these authors, there must have been previous works, right?
Many works actually.
Many works.
Many papers. So the history is that first people treated gases of small density, if the density is sufficiently small, because then not many collision happens. That happened, I think, in 90s by Illner and DiPerna, and I'm sorry, Pulvirenti, Mario Pulvirenti and Illner treated that case. And then people, since the problem was too hard, people introduced randomness to the system. In fact, I work on the random version of the story. I design a system when particles, when they meet, they toss a coin to decide whether they want to collide or not. In other words, most of the time they ignore each other. They just go through each other. However, the number of particles would be much higher. And to motivate the model, imagine you have a gas in dimension 3, and then each particle is a ball, and you look at the shadows of these particles on the floor. So what you see is that the shadows are also moving according to some velocities, but most of the times when shadows collide, the collision is fictitious, doesn't happen. They just go through each other. So inspired by that, I formulated a model, and that allowed me to have a more flexible between the number of particles and range of interaction. So in reality, the range should be this. But if you add randomness, you can enjoy more flexibility. And in fact, I allow a situation when you have something like this. And then I derive Boltzmann equation for all times with no smoothness assumption, provided that this alpha is bigger than d. So in other words, if I assume that particles only with probability of size epsilon minus 2d, so, and you know, if d is 3, this is 6, epsilon minus, epsilon 2d. So when two particles collide, the probability that they go ahead and have the collision would be of order epsilon 6 to the 6. Otherwise, they ignore each other. If you allow that, then I know how to do that. And that happened back in 2000, maybe 3 or something. But I couldn't do better than this restriction.
I see. So in this preprint, what is the type of, is there a general idea or a new method that these authors introduced that they can?
Right. So there are many things going on. This is the classical picture. Classical picture means that this box, you start from Newton's equation. There's a quantum version of the whole story. In the quantum version, you start from Schrödinger equation. Then all these stories are valid. However, the progress is even slower. So all
in this work, they have no randomness. Is that what
There's
you're
no
saying?
randomness, but you can start with a quantum world, quantum version of these.
I see.
So microscopically, they're interacting via waves. And then there is a wave version of it. There's something called nonlinear Schrödinger equation. So Schrödinger equation, the size is enormous. I mean, imagine you solve a Schrödinger equation with this many components. This is a huge differential equation to solve. So there is a version of it when you do some averaging and you reduce the size of the system, but then you have have to deal with nonlinearity. There's a version called nonlinear Schrödinger equation. When the dimension, the size, reduces drastically. When that happens, there is also alternative formulations of all this kinetic theory. It turns out that that formulation is easier to do kinetic theory. So these authors first took care of the quantum part of the story when interaction is mean field. Mean field means the interaction is in average. It's not like particles have to get close to interact. Everybody interacts with everybody else, but the interaction is very weak. When you do that, mathematics simplifies. First, they figure out how to do the quantum world. And once you have that, then you have a new intuition. So he had this experience that was very unique to this quantum world. And they managed to show that the idea there can be extended to this. But for that, they have to compare the particle density directly with the solution. And you need a nice solution to Boltzmann equation to make that comparison feasible. However, so that's the assumption. They have to assume there's a smooth solution. This is also a long-standing open question. We don't know how to settle that. Nonetheless, this is enormous progress.
Extremely interesting. Thank you very much.
Sure.
Thank you.
Yes,
Thank you very much for your very interesting talk.
My pleasure.
I think you mentioned that in some of these limiting processes, the theory, the rigorous result depend on the existence of classical solutions.
That's right,
for both
like
methods.
this work. That's right.
And you, if I understood correctly, you say that results on classical
Nobody-
solutions are not
Nobody has the slightest idea too. There's a weak solution, but that's not good enough.
weak solution. And my question is there anything known about the possible existence of similar solutions for both?
So weak solution means you allow singular solutions. So that's pretty plausible, but that's not the issue. The issue is, so there is a work of Depernod-Lyons. In fact, I use Depernod-Lyons solution to do the derivation. So this scenario, I derive Depernod-Lyons notion of solution. Depernod-Lyons is very weak. It's so weak you cannot even verify the conservation of energy. You don't know the uniqueness of the solution. The idea, Lyons later proved that if you have a classical solution, then the weak solution coincides with it. So you have uniqueness if there is a classical solution. But then we don't know how to prove the existence of classical solution. The idea is that if initially you start with a smooth function, smooth density function, then the solution must remain smooth at later times. We don't have the slightest idea how to do that. And the problem is the estimates that are available are the estimates that were discovered by Depernod and, discovered by Boltzmann. We haven't been able to do better than Boltzmann after so many years. The estimates are based on conservation laws, the entropy, the H theorem, which says that if you differentiate the entropy, you get the entropy production. So you have conservation laws, the bound on the entropy, and the bound on the entropy production. These are the estimates that are available. We haven't been able to do better than that. But Depernod-Lyons managed to use the existence estimate to prove the existence of a very, very weak solution. But we don't know how to do better than that.
Okay. Thank you.
Thank you very much. I would like to make some ignorant question. If people of the street listen to that, they say that things work in engineering. I think that my daughter is engineering, and maybe in third year of engineering, they explain this equation for the gases and fluids.
Right.
And they don't have easy to have some solution. How in the practice things work?
You can do simulations. You see, we are flying planes, missiles, everything based on fluid equations, and you have gases.
Toilet,
You can do simulations.
Yeah.
And you can kind of do simulations and produce solutions. But then when it comes to mathematical questions and things like that, then we are stuck. Well, otherwise, we are not going to stop living because there's no classical solutions. So that's the idea. You can still do a lot of simulations. So in fact, all the numerics classes we teach in Berkeley graduate is based on how to simulate fluids equation. So they have many methods they develop to do simulation.
And you say this Boltzmann equation is for dilute gases and the other
Right.
one is for
This
gas
is-
and fluids. But
Yeah, this is like denser gas, and there's a version of it called Enskog equation when the gas gets a little bit denser.
But not
and
for
the-
fluids. You have some
Not for
like
fluids.
Brownian molecules that do not collide, no, easily.
Brownian, the Brownian things comes in Navier-Stokes description. Navier-Stokes description, when you want to describe the viscosity, then microscopically the particle not only has solving some ODE, it also experiences fluctuation. That fluctuation is modeled by Brownian motion. That is the Navier-Stokes side of the story. But you don't encounter it here because this is too dilute. When it's too dilute, most of the time the particle is traveling freely with no interaction. Once in a while, you know, just change directions. That's why this picture is valid. Otherwise, it's not a good model.
Thank you very much for your splendid conference. And un aplauso para el conferenciante.